Okay, so this is the last session, and as I promised you, we have some system control here. I hate the word control theory, which is the pedagogical term on any of this kind of matter what you are looking at on any university in anywhere. Since control theory is like a military intelligence oxymoron, since control, the theory part is just a mathematical tool set, but anyways you are just applying it. It's very applicable engineering technology. It's not really science. Unfortunately, most of the books on control theory are written by mathematicians who really love the all kinds of mathematical parts of it. And yes, it's very beautiful if you look at the mathematical part of it. But anyways, another thing, I also noticed that, okay, this course has been a little bit heavy. Right, on the heavy side. So it means that basically the individual exercise what I was planning to have also, now it's cancelled. And more stuff coming up, yes, but not for this course. This is already full. I think that everyone agrees that this is kind of full course already. Plenty of things. On the other hand, it has only few things. I actually am planning to go through some of the things that kind of review what we have already done during these 6 weeks. What kind of things has been done. But anyways, this is full, meaning no individual exercise. And today we go through the control. But anyways, I already updated the scoreboard of the course, which shows the percentage. And my scaling for this scoreboard is that 40% is 1. Passing grade is 40%. Number 2 is 60%. Number 3 is 70. Number 4 is 80%. And to get 5, you get 90. You must have 90% of the points. All right. If you want to actually better grade, then you can take a recit on the next 2 recit days available. So you can try to improve it by a recit. But I must warn you, the only way actually to make a test is you would have a lot of pen and paper calculus instead of MATLAB. Sorry. Okay, but anyway, so back to the business. So control, but before that, let's go through this stuff on whiteboard. There we go. So what to remember from signals? So this is basically kind of review. Signals. Most important part of what you remember from the signals is that we actually handle sampled data sets. Where we have, and now you might actually want to stop playing with that stuff. Sure, it's alive. All right, but anyways, so we have x of t, continuous time system, and then we actually, when we sample it, we just take the sample such that you have index n, which is just a running number or index number times sample time here, oops, sample time, which is also 1 over the sample rate. Okay. Signals, and then that signal and two other signals. One is impulse signal, delta n, and then we have the step signal, mu of n. Okay, that's more or less everything about the signals. Then signal spectrum. So this actually is as a function of time, but the spectrum is actually just the same thing as a function of the frequency. And from signal space or the time space to spectrum space, you have a Fourier transformation, namely fast Fourier transformation, which gives you the signal spectrum from 0 to sampling rate over 2. And that's actually the presentation of the signal. While here we have the values at certain time, here we have the power or magnitude at the certain frequency. But still it's the same signal, just representation on frequency space. Okay, and then actually we usually have a more interesting than just single more interesting signals than just a simple spectrum could do a respect to that. Basically, then actually we can calculate the spectrogram of signal, which is simply the showing how the spectrum is changing over time. So here we have the time, and on vertical axis we have the frequency. Oh, actually, let's mark it omega. And time, and basically it shows a color-coded image how your signal is changing by the time. Spectrogram. Okay, good. Is there anything else on the signals? Maybe, but well, let's move on. On the system, so if we're talking about linear time invariant systems, we had also this one small exercise about when system is linear and time shift invariant and causal and whatever. Stable. Linear time invariant systems basically can always be expressed as the difference equation which has the sum k from 0 to n bk times x n minus k minus k from 1 to n a k times x, well, not x, y k minus n, okay, which is actually the data and its history and the history of the output, and basically these terms are the filter coefficients or system parameters, plenty of different names. And showing, okay, k from 1, meaning that a0 is always 1 on this kind of representation. Okay. Time space, you have the difference equation, and you also have the block diagram. Block diagram, which is basically a implementation of the filter, how the calculations are actually done. So this is implementation. So direct form transposed filter implementation would look like you have the input to the summation, then to the other summation, that's the output. Yes, and the feedback actually, no, not feedback, but the delay chain is here, so on. Let's see, goes more or less like this. I think I'm missing one gain block here. Yes, I'm missing one gain block right here. And like that, and then this is not so important, so I'm just scribbling it A1, A2, B0, B1, B2, and so on. So okay, that's the implementation, how you implement it. And this direct form 2 transpose means that it has just one single delay chain which takes care of both the history of xn and yn. Okay, so that's basically everything about the system presentation itself on time space. Okay, on frequency space we have transfer function. And if we had this A and B just like here, B and A here, the transfer function of the system is, oops, B, oops, times zeta minus k, ak times zeta minus k. Numerator polynomial, denominator polynomial. K from 0 to n, k from 0 to n. Okay. So this is the ordinary way of showing the transfer function, where we have the same system coefficients A and B right here. Same as in the time space difference equation or block diagram, meaning implementation, we have also the transfer function, exactly the same coefficients. And then we can also, since this is a polynomial of z, we can also show it as the zero and pole form, where we have not sum anymore, but a product. And for nth order polynomial, we have exactly n roots, z to zk, z minus pk. Whether that's the difference of the whatever point in the complex plane to zero location, and same thing for the poles. Okay, and that was just a mathematical trick, although that gives us the zero pole plane, bk divided by ak, I think it's here. And we have the Argand's diagram, or the zero pole plot, giving the zeros usually on the unit circle, if this is circle, the filter. And then the for IIR systems we have the these poles are actually on inside of the unit circle, then it's stable system. Okay, good. So what else? Then from the transfer function, actually, we can calculate the frequency response, which is simply, yes, and simply, since we have a way to calculate with the complex numbers, we just take e to j omega, which is basically the unit circle in z-plane, and calculate the transfer function on unit circle. So that's the frequency response. And frequency response has two parts. One is the absolute value. So this is the amplitude or magnitude response, maybe like that, and again the physical scale from 0 to Nyquist rate. And then it has also this phase response, for example, like that. Okay, actually the 0 goes somewhere in there. Negative phase shift, meaning the delay. So this is the theta of omega. Okay. So that's about the analysis of the systems, So meaning that those are inside of unit circle, the system is stable. All right. Let me take a couple of pictures and then go a little bit forward. There. Then we actually go to the applications, or, well, wait a minute, we had also the system responses, yes. So that's just one part of the responses, how to calculate the frequency response. Another very important responses for these systems are actually the impulse response and step response. Impulse response meaning that whatever your system is defined by transfer function. Okay. When you feed in the delta function, you get impulse response out. Okay, that's always the case. Nothing more into it. In addition, sometimes we need to also take a look at the step response, and especially today when we are going to the system control. There we take the step input to the system and see how the system reacts for that kind of signal. Meaning, for example, or on this control systems, you want to raise the temperature of the room from 16 degrees up to 21. Okay, you usually just give it a command. Now increase the temperature that much. And then the system should take care of the control and increase it. All right. But if it's a depending on the system transfer function, you might actually end up having this kind of behavior on your system. Quite common. You have some overshoot, some ringing, some settling time. For control systems, the step response is very important factor. For filter systems, impulse response is actually the one which defines the whole system. And on impulse response, we have two categories: finite impulse response systems and infinite impulse response systems. These are simple to implement. You need only the convolution. These actually require a little bit more of the considerations, especially the stability. Okay. So, FIR filters, we're talking about filters. The design started from low pass filter on continuous time, transferred into the Z plane. Oh, actually this is the frequency. Continuous time low pass filter on frequency space looks like this one. It has a cutoff frequency Fc with inverse Fourier transformation that transforms into sinc. And when you sample the sinc, basically you get FIR impulse response. Something like that. But when you sample it, you actually have the sinc and the window function. Okay. And basically, to control the system stop band, you need to smooth the sinc. And there you basically had the design parameters, cutoff frequency, which goes to Fc over, is it Fn? Maybe, times sinc n times Fc over Fn. Okay. That's used to set the cutoff frequency. Then we had the stop band attenuation. Actually, that defines the window form or shape. And then the last one, the transition bandwidth of the filter is defined how many points you take for the filter. So it's from minus n to some other n. So this is the width of the window. Okay. So those parameters, but anyways, then you can define the low pass filter and then the other filters by modulation. Modulation gives you let's see, but and addition. So modulation gives you high pass or band pass filter conversion. If you add high pass and low pass, then you get band stop filter. That's all you need to know. So FIR filter design, quite simple, using windowing method, but then with the IIR filters, basically where it starts from is the I usually start from here, explaining what it requires. So basically we need to optimize the parameters such that the zeros and poles are such that that we get the desired the behavior of the filter. Desired behavior, and these are the say optimized methods what you can find from the FDA tool. In MATLAB. Okay, so that's the third way of doing it. The second way of doing it was the classical filter and bilinear transformation. And there you actually have, since the classical filters have a lot of history, and they are also quite straightforward design. There are also some methods how to estimate which order number you need for certain properties. So basically, there was that tools field plus field ord, I think, or butterboot ord, that kind of things. But anyways, so that's how you design the IIR filters. Except that one, which is the stop and notch filter, the only filter you can actually design by pen and paper on IIR filters. Okay. Good. Let me take a quick look at. Yes. Last time we actually had one more, say, more advanced topic, which is what happens if our system actually cannot calculate floating points, and then you have these rounding effects. And also you get involved into the stuff Keijo taught you in modern computer architecture class. So the embedded stuff. Couple of things there. First one, of course, is the performance. That limits the how big filter you can use. Practical limitation for how many calculations you can do for a single time step. Order number of filter, yes, order number. And then the calculation inaccuracy actually practically means that the higher order systems are always divided into second order sections. So meaning those will go to cascaded second order sections to actually have good computing accuracy even with limited number of bits. Okay. And now we can go into, with this quick review, we can go into today's topic. Not that one. It's a system control. Ooh. Yeah. Yes, it's nice. And it's very expensive. And even more expensive to actually keep it in good condition. It just needed new brake discs on the front, of course, then the brake pads, and then also now it doesn't have any lambda sensor anymore. Who needs lambda? Which means that it's a little bit tuned up. At the same time, it's a lot of fun now, and very expensive to keep in running condition. Okay. And yes, actually this already has drive-by-wire gas, the accelerator. It's just, it still has the ordinary, what is that called, the wiry, whatever that is in English, it's kaasuwiring. It still has some steel wire to but not anymore into the motors directly, but it actually just controls a potentiometer. And the rest of that stuff, the motor control is in the control box. And this doesn't have the Bosch shit. It has, you know, some better Marconi system on it. Not standard. Okay. There's nothing standard on that bike, in good or bad. Okay. So, yeah, this system control sometimes, or almost always, this is related to the control theory. We have some exchange students. Have you had already your control theory classes on your university? You're from Germany, right? No, you're not Germany. You are from Germany. Does it still?
Unfortunately, we had it.
Yes, you have it, and it's heavy. Did you already take it?
Yeah, the complete control theory in one term.
Yes. Yes. So basically, these are lucky. They get the full control theory in 2 hours. Consider yourself lucky.
We didn't do any practicals.
Oh yeah, yeah. Yeah, but it's very practical stuff, since wherever you have system control, you're actually somehow applying already the control theory. And it's a little bit too much mystified kind of thing. Okay, but I think anyone who has tried to take the control theory classes know that it's considered to be very hot topic. So we are not going to any details on how to actually do the final implementations. That's a little bit heavy, and it's not that heavy. It just requires a little bit more time than we have in this class. However, I added this system control on this class basically for a couple of good reasons, but one is that it's actually an implementation of FIR system. So, not FIR, sorry. IIR, Infinite Impulse Response System. Okay. And there are actually, I found a couple of good books. Westcott, Applied Control Theory for Embedded Systems. Yes, it's applied. It's very close to the book that I would write if I would write any books. So it has very practical point of view. It has real life examples, sort of. Okay, and the other one is good review of control engineering overall. So basically, on the control theory or control systems, we have two sorts of control. One is open loop, so that's kind of, I wish that, for example, temperature was this on the classroom, but I would have no other than that big wish there. No feedback of measuring the temperature or something else, but just to send a command, okay, now do that. The same way, actually, I would guess, do you have feedback on your system when you are trying to control the speed? Okay, yeah, that's why it fails. Okay, if you don't have any control or any feedback from the system, if you are not measuring any speed or position or something like that on your system, you don't know how the system is behaving when you're sending a command. And yes, very limited control. But anyways, a classic example, electric block heater for a car, which is just a timer, or actually it's just a heater element, and you time it externally with your, that block heater outlets. And then you can also burn your car with that, practically. Closed loop controllers, those are the ones which has some sort of feedback from the, so it measures the outcome and tries to adjust the system such that it actually gets there. So all control systems which use feedback, or practically all do, and generally those are then IIR systems. If you add a thermostat or something like that on electric block heater, then it becomes a closed loop system. So it has a feedback, it cuts off the power before your engine block water starts boiling. Okay. All right, and that's what a generic just a moment, I think I need to check that everything is going to the tube as I wish. Yes, they are. So that's how any closed loop system control actually would look like. So the controller is the one that you would be designing to match the requirements. The plant here, that's an old term from the era of the steam power, actually. The term is actually from steam power control. Those are, by the way, just magnificent things how they stopped the train steam power plants to explode. That was a small problem on the beginning of the steam engines. You could actually overheat the steam plant and then it explodes with a big bang. But anyways, those things that were done to prevent the that kind of things, those are just wonderful machines. Okay. So, but anyway, so we have a controller which has the control signal going to the plant. The reference is actually the value that you would set. So the system should set to that value, meaning, for example, that 21 degrees. Then you have a controller with output is somehow directly driving the plant. So it's the signal to the plant. And in between control and plant, there is a disturbance signal, meaning that if you have some external effects, they would actually would be calculated as the disturbance to the control signal. Okay, those disturbances are usually inside of plant, but this is how we model it. This is just a model, and it works. Okay, and after the plant we have the output, and that's measured, and we have the feedback there, and there we have a summing junction on input basically, and as you can see, it has the error signal is actually running the controller. For example, on heating, do we need more heating or not? Or do we need cooling? Heating or cooling? If the error signal is positive, our reference is bigger than our feedback, meaning that we need to still push more signal. If it's negative, then it means the feedback loop is already giving higher signal. So basically output is higher than what we required. And the transfer function looks like that. In practice, these systems are mixed discrete time and continuous time systems. The plants are almost always analog in some point. In some point it's analog, meaning a real life kind of system. Sensors may be analog, then it requires the A to D converter, or it could be digital, so it has the A to D on board already. Or actually the sensor can be also digital. For example, these devices that are actually just measuring the rotation speed. They are just optical interrupters or something like that. So you get certain number of pulses for each revolution. Okay, that's digital value already. And then the control software actually is in some sort of embedded controller system. And then the drive is, well, somehow you need to drive the plant anyways as with the analog signal at some point. Okay, but there's a digital to analog conversion and some amplification or some driver circuit there. Okay, so that's fundamentally how it looks like. And some of these are analog systems or continuous time systems. Some of these are, well, the control is a discrete time system, and there are some considerations. Some considerations. For example, the simple that if you have very rapid changes on the response, you need to sample it fast enough. Okay. Okay, some tools. So we have the first tool is called step response. Just a moment, I'll check which pictures I have. I have that one already, so I don't have the embedded. For the step response is used on with the controlled systems to find out if a system actually behaves nicely. Meaning that whatever the system is, you would just send the that's the system transfer function and check what is the output. And basically from the output there are some parameters. So generally the output would look like something like that, where the let me mark some important parts. the system DC gain is actually the value where this one settles to. Yeah, DC, meaning no changes at all anymore. So basically at here and beyond, this would have been settled. So this then defines the DC gain. When you wait long enough, that one to settle. Okay, then we have the rise time. Rise time means the 90% of the final value. And if that was the time of the step, then you would actually calculate it from here. So at 90%, that's the tau r, like rise time. Delay time, meaning basically how long delay the output would have for the input. And basically here it's defined. The definition is when the signal has changed 10% of the full DC gain. There. 10%. So that's the tau d. Delay time, rise time. Overshoot. Overshoot is maximum value where the output actually reaches after the input, or this one. So this is the overshoot. Or actually, this part is the overshoot. And it's usually given as percentage. How many percent overshoot the system has. Settling time, and here settling time actually, IIR systems never settle. Okay, so it's settling time to some certain the region. Let me mark, for example, here. Some plus minus some percentage settling time. And that's actually, for example, here, that is the last point it goes over the settling time. Tau is. All right. So if this was a temperature control system for room temperature, then I would be happy with 10% accuracy on the room temperature, or actually I would be more than happy with the 10% settling the region. If this was a speed control on, or actually if this was the controlling the AC output of a power plant, that would be 6 sigma or something like that. So 0.000 some 6 zeros and 1, which means 4 zeros and 1%, so 0.0001% accuracy on the frequency. Okay, so those are the common parameters that are delivered for the any control system for some application. All right, and well, that's just a using the step response. You can also figure out what is the system impulse response by differentiating the input. Basically, if you take this step response and minus or step this step, then you would get the delta, and this would give you the unit impulse response. but only if the system is linear. Okay. Good. And the same thing on a picture. Hey, it looks more or less the same. Another one. This is probably something that I see some hair to stand up. Right. Final value theorem. That requires some calculus when you do it by hand. Yes, it does. But anyways, basically this is the fine way of calculating the DC gain of the system. So final value theorem actually tells that you don't need to wait for the infinite time for calculating what is the last value of the system, but you can actually deliver or derive it from the Z transform of the signal, meaning the transfer function of the system, control system loop transfer function. You multiply that transfer function with that Z minus 1 divided by Z, and then you multiply it by step function. Then you get the final value simply by checking what is the value of transfer function when Z equals to 1. Okay. And there was also a notification that controlled system step response should always approach the expected reference value. Okay, yeah. So otherwise it doesn't control. Then actually you might end up also playing with the blocks. We already had this with the filters. So if you have two parallel blocks, then basically the system transfer function for parallel blocks, you just add the transfer functions. Okay. On cascaded systems, that was the way we did this. Second order section division, we had cascaded second order systems that actually gives exactly the same transfer function as the original. Okay. So that's how you calculate those. This is basically a little bit, well, it's not that hard either. On this analysis of systems, sometimes you need to change the order of summation on block diagram. So block diagram, how to move the plus block. So consider this sort of system. Basically we have here, for example, x1z and x2z. Okay, these are the Z transform signals. Exactly the same thing as I would say here, x of n, x of 1n or x of 2n. You can do the calculations similar way. And whenever you have the system, then it just becomes easier to calculate everything on the Z plane, because basically here you have just x1z plus x2 z, and at output you have g set z times that one. With the transfer functions, the power is that whatever is in input, you just multiply with the transfer function and you get the output transfer function. The same way we did it for the filters, we have the x of n, h of z, y of n, but at the same time it's also x of z times h of z is y z. Actually this is just x z times h of z. So basically this simplifies the transfer function presentation, simplifies the analysis of these complex systems. You don't need to worry about time space kind of formulas anymore. Just simple multiplication. Otherwise you would be dealing with a lot of convolutions, and convolutions are nasty. Okay, but anyways, so x1z plus x2z, okay, which is the same as gz times x1z plus gz x2z. Okay, that would look like a system where you have the gz here and here, and you sum the outputs. There. Okay, that's why the first movement is like that. Same way, if you had only on the lower graph there, so if you had the transfer function only on one of these blocks or one of these signals, you can basically move that one. Let's see if I can do that. I need to take a couple of pictures again. You're allergic to transfer functions. Okay. All right, so we had the same thing going on x1z to g of z, and that to summing junction, and basically the other one input here is x2z goes to summing junction, and that's the output here is g of z times x1z plus x2z. And if we want to actually somehow have the common multiplying factor like in here, if you want this kind of on the output, you can mathematically say g of z x1 z plus g of z times g1 g minus 1 of z. So this is the inverse transfer function x to z. So if this was a numerator divided by denominator, this is actually the vice versa. You just swap the numerator and denominator. One warning about that one. This is simply an analysis tool to reduce those or calculate the total system response. Do not ever design a system which would require a real inverse transfer, since that does not necessarily even exist, or it could be very unstable, since now your zeros of the original system will be poles of the inverse system, and the inverse system poles on unit circle. You would have a very critically stable system, or even better, if you have a FIR system, for example, with the zeros on both sides of the unit circle, then you would have plenty of instability on the 1 over the inverse transfer function. So this is just analysis tool to analyze a existing system. All right. But anyhow, now we can take the g of z here as common multiplier, x1z plus g minus 1z times x2z, which gives exactly the what I had there with x1z, and then we have x2z, and then we have the system 1 over gc, like that, and output has the common block there. Okay, but anyways, now we move the summation point to the other side of the transfer function. All right, so next point of playing with blocks would be loop reduction. Loop reduction. So wherever you see a loop, you can actually go and just take loop off. You just calculate the transfer function of that block as it is. Okay. Loops, oops, input summation, or actually this is the error signal, usually GC. Let's mark this one with AZ, although this is the feedback. Well, I will just mark it F. FZ, all right. FZ, and basically everything starts from here. XZ, YZ. Here we have XZ minus FZ times YZ. And here YZ equals G of Z times XZ minus FZ times Y of Z. And with simple math, let's see, YZ plus F and GC times FZ, right? Am I correct with that? Times GC times X of Z. Yes, I'm still okay. I might actually even get the same result. Wait a minute, YZ. Yeah, so on the left hand side, YZ times 1 plus GC times FZ equals to GC XZ, and then the system transfer function is always YZ divided by XZ. Okay, move that one here, this one goes there, we get G of Z divided by 1 plus GC, oops, FZ. Simple calculus, nothing fancy about this. And I'm done with this. Good. Let's take a quick look at the our kind of the generic form of closed loop system control loop. So fundamentally it looks quite like this one, except that here the GC is controller times plant. C of Z times P of Z. Yes. There I have a continuous time presentation, but same way discrete time approximation would be PZ times CZ divided by PZ CZ times F of Z. Okay. Where did I forget the disturbance? Nowhere. Although the systems, any system usually is quite non-linear. For the control point of view, it's usually if you have the short enough of time step or the enough of resolution, then you actually end up being quite linear on that control point. So basically you can do a kind of assumption that okay, for the control point of view the system would be linear, and then it would have the linear the behavior, the whole control system would be linear, which means that you can actually apply the superposition principle. Superposition principle is the best thing after invention of wheel, since now you can actually take each of those signals and analyze them separately. In control system, it's quite nice behavior, since now you can actually so let's see this u. That's just u. Okay, u minus plus, that's the error signal. Direct feedback, meaning we have an ideal sensor with no feedback, this one transfer function, meaning that it directly measures what it's supposed to measure. And then we have this z of c, and this one is the p of z, not planned. No, that's I will take a shortcut on that one. So a of z, there's the actuator, meaning that you, in addition to the this control, this is usually the driver is separate and it has its own transfer function. Okay, but here's included there. All right. That's the disturbance signal. UD. Okay. And then we have the plant feedback like that. For input output, oh, that's why. Transfer function for input output relationship. U to Y would be same as in here. Also, although the GC here is the PZ times Z of Z. Superposition means that basically in this case we just turn this one equals to 0, so this is just a common line, okay, which means that we have the system transfer function for the controlled loop would be simply G of C is ZC times P of Z, okay, 1 plus ZC times P of Z. Okay, very simple transfer function. Good, but how about transfer function for a disturbance signal? Meaning how much the output reacts for certain disturbance input. I'll just draw this one separately. If we turn U to 0, this summation becomes only the minus number. So output would be, this E signal is actually minus output signal. So -1 times CZ. So that's our, now we have plus and plus, UD, plant, and Y. So, okay, the same way again, except that now we don't have that minus here. So it looks like this is almost like the feedback loop without that sign. Or does it have the sign? Yes, it has the sign too. Sign is actually minus CZ. So it actually the minus can travel from here to here. So it's exactly the same feedback loop as we had on the original. It just looks a little bit different. We have X of Z is here. There's a difference to the feedback, and PZ meaning that the transfer function for the disturbance signal UD to Y, meaning U equals to 0, DZ, yes. Does it come the same? Something funny about it. No, it's not the same. It's the yes, it is the same. Not always though. No. Yes, no, sorry, yeah. So CG is now the feedback, right? And that's that one. So we have the PZ is the plant, or that one. This part is the CZ, so we have the CZ times P of Z. Okay. So this is how you analyze the disturbance, how disturbance actually, what it does for the system. This is how you design your control. So for control, actually, you try to get the system going as fast as possible and settle as fast as possible to the desired value. On here, what you would like to have as little as possible effect from the disturbance signal. So basically, for a good system, the step response of disturbance signal should look like that. As little as possible, the ringing effect there, and settling as soon as possible to 0. Okay, no effect. Good. And then some. Good. All right. Basically, there are 3, I would call these classical controller systems. So basically, we have PI, or PID controllers, and in some very rare occasion, we actually may have PD controller. Anyhow, what are those P's? Just a reminder of that closed loop system control. That's what we are talking about. And now we are focusing on the controller. plant is what it is, feedback on the control output, that's also what it is. Now, what is the controller? So basically, proportional control is simple one single gain block, meaning that since basically after the reference, there's a difference between control and reference, you would actually use the control signal which is directly proportional to the difference, meaning just a plain single value. So that's the simplest controller type. You would just feed in the system, and basically what happens, I will draw you a small diagram here. What happens for P controller? And for step response, if you're running a step response, and you have this nice graph of the so that's your reference value or desired value there, okay, which is also the same as a DC gain, should be 1, okay. And at the beginning, when you start driving, the plant always has some for example, the heater, that's very classical. When you start to heat, when you start boiling water, nothing happens. On the beginning, you are right here. Although you have turned your stove to the highest possible, nothing happens, but actually it starts heating. And basically, after heating, this part here is your error signal. Okay? You continue heating, but use that one as the feedback term. So next time you heat a little bit less. I know this sounds a little bit funny, but the idea is that when your signal is getting bigger, the error signal gets smaller, and basically that prevents overshooting. Okay. But another thing that P control does, your system, if it's first order system, so natural system with just some slowness on the natural slowness on whatever the plant is doing, heater is excellent example, or anything that has mass, basically anything that does not vibrate by its nature, then this one never reaches the reference value. It goes closer but never reaches the reference value, and that's why you cannot find the proportional controllers in real applications. But however, this is almost guaranteed to be stable. If you just would keep heating until you hit here, your system has some slowness and it starts ringing, and that would actually mean that you are boiling your pasta with too high temperature. That would be disaster for Italians. Any Italians here? No. Good. All right, but anyway, so the P controller has just the controller. The transfer function is a constant, Kp. All right, but this is the most commonly used controller in industrial applications. All right, it's proportional integral control. Basically, this PI controller, let me see if I can fit all of these three here. PI controller, while this P controller decreases the signal, the error signal is decreasing while we are getting closer. Actually, this one has a smart way of calculating also the integral of the error signal, so that we actually start adding up. So if the output is say longer the output is on either side of the control or the reference value, the integral proportion will come greater and it starts pushing it more into that direction, closer to the final value. Okay, so and there we have a, say we still have the, so PI meaning it still has the proportional part of it, part of the control, but then it also have the integral of the error signal, and that's how the fundamentally the integral is marked. If this was a filter, it will be very unstable, or it will be critically stable filter. But this is not a filter, this is system control. And having this one inside of the controlled loop actually gives very nicely behaving stable systems. Okay, so that one is part of the step response, meaning, well, it will be here, the CZ, here ZZ, or on the transfer function, it will be here, and with some nice nice properties. So it starts about the same, then the integral starts hitting. Error on this case, it probably goes something like this, maybe a little bit overshoot, and goes like that, the final output, because part of this error signal is actually integrated. So the difference is actually, well, let's see. While on the original P signal would go something like that, but the integral part actually, will be something else. Okay, can't show it exactly, but anyways, that's the most commonly used. Although, and yes, the couple of things why it's most commonly used. One, it usually does the trick. Second, it almost never goes unstable. It's quite simple to tweak. It has only 2 tweaking parameters. You can find the region of the stability quite easily with this kind of PI controller. And when you are optimizing, it's easier to optimize just 2 values than 3 values. And usually this is, say, close enough controller. Although the mathematicians and say engineering teachers, they love proportional integral derivative type of controller because it's so beautiful. I haven't found any other reasons why anyone would like PID controller. It actually gives some speed for the disturbance, transfer or disturbance effects. Since if this basically this one feeds back some derivative of the error signal, meaning that if the output changes rapidly, and it usually changes rapidly only because of the disturbance, since you have all the power to run your control not just step but also with the ramp, so you can stabilize the input for the system, but you cannot do anything for disturbance of the system. So for highly disturbed systems, which basically are, say, on industrial applications where you have a very demanding system which has some of these systems are very closely related to others, so one system start will happen will cause also something else for the next system. For that one kind of complex systems you would need PID. But for example, on those motor controls what you are playing now, PID will be overkill, since you do not necessarily have there the external disturbance. Okay. But anyways, so another. So on this PID controller, we still have the integral and the proportional part, and then we have also the derivative part, which derivator actually is, well, it's the inverse operation for the integration, right? Z minus 1 divided by Z. Okay. So basically this gives fast recovery from disturbance signal if it's designed correctly. If it's not, then it actually starts behaving badly after the disturbance. Okay, couple of things. So this derivative part, so that was the integral, and this was just proportional, and that's the derivative. Derivative also is also very sensitive to high frequency errors. So meaning, okay, let's put it here, but noise sensitivity, that's maybe the worst caveat of this kind of controller. Noise sensitivity, it's opposite to integral. Integral integrates also the noise, and if you have a normally distributed noise, it basically averages to 0. This is the inverse operation, meaning that it enhances your noise by factor of KD. So if you have some noise between adjacent points, data points, then it will be actually the most evident factor on this controller, meaning that you either have to use a small feedback term or the small gain for this part, or do a bandwidth limitation. This is the ultimate high-pass filter, meaning that you would use a say band limited high pass filter. Okay, let's see. Can I actually draw this one? So originally, this filter would look like, well, that kind of thing. On the frequency axis, you would do bandwidth limit. So it would be high pass, but limiting the highest frequency components. Then it would actually work just fine. So that gets some of the noise sensitivity out. But anyhow, the another point here, while this only had 2 parameters to fix for the optimal performance, now you have 1, 2, 3 parameters to fix the So it's will be of order of magnitude bigger problem to find the optimal parameters for PID controller. But it can be done, it has been done, and it should be done if the system is complex. If it's a simple system, that's your choice, PI. Or you can always play with the PID and then just turn the KD to 0. All right. So that was the theory part. It is a little bit heavy. I hope you enjoyed it. So did you enjoy? Welcome. I need a short break here. So after the break, or should we have a lunch break? Lunch break until 1:15. So 1:15 I'll start with the lab tutorial. Good.